Hello there. This lecture is all about continuous probability distributions. So the last lecture we looked at discrete probability distributions when we had a discrete variable that was limited to whole numbers, right? So we looked at the number of light bulbs that would go out in a tanning bed, for example. That's a discrete variable because you can't have a fraction of a light bulb. Well, many business situations are not concerned with discrete, whole number, counted observations, but with measurements that can take on any value. So they could be a fraction or a decimal. So, for example, measuring the weight of a randomly selected box of Cheez-It crackers. You could have a box that's 16.12 ounces, right? It'd be a fraction, it'd be a continuous number. Maybe you are recording flight times and you record the flight time from Las Vegas to Ohio as 4.5 hours, right? A fraction of an hour. Or measuring the amount of time a customer spends on the phone with a Comcast representative. It could be 32 minutes or 32 minutes and 5 seconds or any possible number between whole numbers. So this lecture will focus on those types of situations when you have a variable that can represent continuous values. So I'm going to start off with a general review of some probability terms, and you've seen these terms before, just kind of a refresher. Then I'm really going to talk about the normal distribution and the empirical rule. This should also be a refresher. We've learned about the empirical rule. Remember, it's just those predictable probabilities of any set of scores based on the mean and the standard deviation, really based on the z-score. So we'll talk about that again just as a review. Then I'm going to introduce you to something called the unit normal table. And the unit normal table is really useful for figuring out probabilities and scores associated with probabilities when you do not have access to the raw data, but you know that your data is normally distributed. And then I'm going to do a ton of examples of finding probabilities associated with scores and scores associated with probabilities to familiarize you with using the unit normal table. So these are the same probability terms that you saw for the discrete probability lecture. X just represents a random variable, the variable that occurs for a given selection or trial. It's really the event of interest. In our case, X is going to be the score or range of scores that we're interested in examining the probability of. Then for the last lecture, you saw discrete random variables. So remember, those are restricted to whole numbers. And now we're really focusing on continuous random variables. So we're not looking at the binomial or the Poisson distribution anymore. We are going to be looking at the unit normal table, which is essentially the distribution for z-scores when you have a normal distribution, where the majority of scores fall in the middle and then the curve kind of tapers off on either end, where there's more extreme or less probable scores that are really high or really low. And still, we're going to be thinking about a probability distribution, which is comprised of every single probability for all random variables. And you can also think about this in terms of the frequency distribution, right? So all of the possible scores for whatever you're measuring along the x-axis, and then how often each one of those scores occurs in your data set along the y-axis. So here's a picture of the empirical rule. So you should remember this picture from the Describing Your Data with Numerical Measures lecture when we looked at the mean and the standard deviation. And I'm only going to focus on the normal distribution. So for our purposes, the empirical rule will always apply. So we're always going to have roughly 95% of scores within 2 standard deviations of the mean and 68% of scores within 1 standard deviation of the mean. So you can see here, whenever you have a score that's 1 standard deviation above the mean, it has a z-score of 1. Remember that? Because the z-score just tells you how many standard deviations above the mean a score is. So for example, if we had a mean of 20 in this, and we had a standard deviation of 5 in this distribution, then a score of 25 would have a z-score of 1, because it's 1/5 above the mean of 20. On the other side, right, if we have a score of 15 from this distribution, it would have a z-score of -1 because it's 1/5 below 20, 1 standard deviation below the mean. And you can kind of see this pattern, with each 5-point increase, the z-score increases by 1 point because it's increasing by 1 standard deviation. And then to the left of the mean, for each 5-point decrease, the z-score decreases by 1 point because it's 1 standard deviation below the mean decrease. You can also see that this is a symmetrical distribution and that the z-scores on the right side are a mirror image of the z-scores on the left side. So if you have a score and if you have two scores and you know that the z-score for score 1 is -2 and the z-score for score 2 is +2, both of those scores are the exact same distance from the mean. You just know that the score that corresponds to a z-score of -2 is 2 standard deviations below the mean, and the score or x value that corresponds to a z-score of +2 is 2 standard deviations above the mean. So just, a quick review of z-scores. Another thing about z-scores that I want to mention is that the z-score for the mean is always 0. See, the mean in this distribution is 20. The z-score is 0 because 0 represents a score that's 0 standard deviations away from the mean. And if the score is equal to the mean, then it is 0, in this case, 0 fives away from 20, right? Z-score is 0. So also, if you look at this distribution, you can see that as the score, as x, right? Whenever I say score, I mean x, the x value, the specific score that you're interested in. If I'm talking about a z-score, I'll say a z-score. If I just say score, no, I'm talking about x. So as your score of interest gets further away from the mean, so as it gets further out into the tail, you're going to have a z-score that's the absolute value is larger. And I say absolute value because technically, as your scores get further away from the mean to the left, right, less than the mean, your z-scores get smaller, right? -4 is smaller than -3. But the absolute value, 4, is larger than 3. So as your score gets farther away from the mean, the z-score gets larger. The score is more extreme, has a larger z-score. It's more standard deviations away from the mean. And conversely, or really at the same time, as your z-score gets larger, that score becomes less likely to occur. So x has a lower frequency and is more rare. So you think about it, a score of 40. If we look at where that is on this distribution, right, it falls right here on the x-axis. If you kind of trace up to where it meets the curve, it's in a low frequency part of the distribution. Whereas a score of 25 with a z-score of 1, if we trace up, it's in a pretty high frequency part of the distribution. It's pretty likely to occur. It's, in this case, only 1 standard deviation away from the mean. And remember, the standard deviation tells you the typical spread of scores. So if this typical spread of scores is 5 points away from 20 and you get a score of 25, you are within the typical spread of scores. And then think about it. As this score becomes less frequent in your distribution, it has a lower probability. So you can think about the distribution in terms of the x-axis. As you get farther away from the mean, your x values are larger on the right side and smaller on the left side, right? Because any score to the left of the mean is less than the mean, to the right, higher than the mean. Also, as you get further away from the mean, on both ends, the absolute value of your z-score increases and the probability decreases. So think about that when we're looking at this distribution, right? Only 2.5% of scores have more than 2 standard deviations away from the mean. Once you get out even further, it becomes less likely that, for example, you would randomly select that score at this value from this population. So let's go ahead and take a look at the unit normal table, which is the table that we are going to be using to identify probabilities and z-scores for this entire lecture. So here is the unit normal table. And there are several different columns in the unit normal table, and I'm going to go through what each of them represent. And the table actually provides a nice little picture of what is a body, what is a tail, what is a mean to z for column D, and what is a z-score, right, along the x-axis. Now, I will point out that this table is not available to you in your book. The table that's in your book is not very user-friendly. I prefer this table, and this table will be posted in the module for this lecture as well. Okay, so column A lists the z-scores. So if you look at column A, you'll see z, and then you'll see z-scores gradually increasing in numeric order. So that represents the position of the score along the x-axis. Now, keep in mind that there are no negative z-scores in this table, and that's because the unit normal table represents a normal distribution. And remember, the positive side of the distribution, the scores greater than the mean, is just a mirror image of the negative side of the distribution, or the scores less than the mean. So if you know you're going to be working with a score that's less than the mean, you can just take a mental note that your z-score is going to be a negative z-score. Now, that being said, there's no negatives for probabilities in this table either, but that makes sense because there are no negative probabilities. So for example, if we turn this into a percentage, you can't have negative 50% of scores. There's no such thing as a negative probability, even if you're looking at a probability to the left of the mean in the distribution. Okay, column B. B stands for the proportions in the body. Now the body is simply the larger section. So for example, let's say this represents a z-score of 2. If we wanted to know the probability of randomly selecting something, a score from this data set with a z-score less than 2, that would be all this. That would be a body. If we want to know the probability of randomly selecting a score that had a z-score greater than 2, this would be the tail, the smaller portion. And you would find that probability in column C. So here's another picture of an example between a body and a tail. Let's say this is a z-score of negative 2. If we want to know the probability of obtaining a score that had a z-score less than negative 2, we'd be looking here in the tail. Probability of obtaining a score with a z-score greater than negative 2, we'd be looking in the body, the larger section here. Then column D identifies the proportion between the mean and the z-score. So if we wanted to know the probability of randomly selecting a score that had a z-score between the mean and a z of, for instance, 1, if this was a 1, then we would look in the mean to z column for a z-score of 1. So talking about that example, like if we were looking at probabilities associated with a z-score of 2. So if we were looking for the probability of randomly selecting a score from our data set that had a z-score greater than 2, think about where that would be on the distribution. 2 would be to the right of the mean, and a score greater than 2 would represent the tail. So this would be the probability of randomly selecting a score with a z-score greater than 2 in any data set. Remember, z-scores standardize your distribution, so all these numbers are consistent across any distribution you're using as long as you're using z-scores as a reference. Now, if we wanted to know the probability of randomly selecting any score with a z-score less than 2, then we'd be looking at the body, and that would be our probability. And if we wanted to know the probability of randomly selecting a score that had a z-score between 0 and 2, or between the mean and whatever that score is, if the z-score was 2, that would be our probability, 0.4772. So remember, probability and proportions can be used interchangeably. So you could also say that if we I like to turn proportions into percentages. So 47.72% of all scores in a normal distribution have a z-score between 0 and 2. They're between the mean and a z-score of 2. You could also say there's a 47.72% chance, if we're going to go probability with it and turn it into a percent. So a 47.72% chance of randomly selecting a score from any data set that's normally distributed that has a z-score between 0, the mean, and a z of 2. Again, I'm going to give you lots of practice using this table and interpreting what you're finding. Now, I'll also show you examples where you are interested, so you're not just interested in finding the z-score associated with probabilities, which usually what we do is we'll use the z-score and then we'll convert a raw score, so an x value, into a z-score, and then we'll go to the table to find the probability. Sometimes you're going to do the reverse of that, where I'm interested in what score falls at a specific probability. So you'll be given a probability, you'll find the correct probability in this table, then you'll locate the z-score associated with it, and you'll calculate x based on the z-score from the table, the standard deviation from the population, and the mean from the population. Again, I'm going to give you tons of examples, but I just wanted to let you see what the table looks like before I start describing what the contents of the table are. Okay. So, column A, that's just the z-scores, right? Corresponding along the positions of the distribution. So these z-scores. And again, there's no negatives because if you have a z-score of 1, it's the same distance from the mean as a z-score of negative 1. Okay, so remember column B, proportion of scores in the body. So if you go in the unit normal table, and I encourage you to open up this table right now, it's posted in the module, and look at it as we go through the examples and as I explain the unit normal table. So I'm going to assume that you have it in front of you. If you don't, pause it and get it. And I'm not going to bring the table up. I'm just going to show the values from the table right now on the screen. So if you go to the unit normal table and you find a z-score of 1 in column A, that represents a z-score of either 1 or negative 1. And if you look at the proportion in the body, so if you find 1 in column A and then you scroll over to column B, you will see 0.8413 in the body. And that would represent the proportion of scores that have a z-score less than or equal to 1, right? All this. Or the proportion of scores that have a z-score greater than negative 1, right here. Now, you'll typically see me display these as z-score less than or equal to 1 and then greater than 1. So you'll see either less than or equal to or greater than. And that's because the table functions with cumulative probabilities. So if we're looking something that's at a score or to the left, right, less than, then we are including that score in that probability. So the probability of randomly selecting a score with a z-score of 1 or less is 0.8413, and the probability of randomly selecting a score with a z-score greater than negative 1 is 0.8413. Now, you can see that I'm essentially confirming the empirical rule, right? Because if you take 0.68 and add it to 0.16, you're going to get 0.84. So this is confirming that, right? Because if we say, all right, the probability of randomly selecting a score or the proportion of scores, the z-score, greater than negative 1, this guy right here, 0.8413, that includes these 68.68, right? 68% of scores that are within one standard deviation of the mean, and it includes the scores with the z-score greater than 1 or that are more than one standard deviation away from the mean. So add those together and you get 0.84 within rounding error of what you see here. Same thing over here, right? The proportion of scores, the z-score less than or equal to 1. So all these, 0.68 plus 0.16, 0.84. So I'm just confirming the empirical rule using the unit normal table. All right, column C, looking at the tail now, the smaller portion of the graph, or the frequency distribution graph. So this would be, for example, right, because we're going to be looking at all sorts of different z-scores, but for now, let's just focus on 1 and negative 1. So the proportion of scores with the z-score greater than 1, 0.1587, so within rounding error of 16.16 or 16%, less than or equal to negative 1, so negative 1, less than or equal to negative 1, same exact thing, right? Remember, mirror image, no negatives in the table, but you can go to the z-score of 1 if you're looking at a z-score of 1 or negative 1, and you're going to get the same exact answer. So now if you're still looking at a z-score of 1 in the table, and you're interested in the proportion of scores between the mean and z, well, you can look at this. So between the mean, it has a z-score of 0, and a z-score of 1, you have 0.3413 is the proportion of scores between a z-score of 0 and 1. So if you calculated the z-scores for all your scores, 34.13% of those scores would have a z-score between 0 and 1. Same thing on the opposite side. So 0.3413 is the proportion of scores between a z-score that have a z-score between negative 1 and 0. And if you add those together, you get within rounding error of this magical 0.68 or 68% of scores within one standard deviation of the mean. So the unit normal table, remember I mentioned you can find probabilities associated with a specific x value or range of x values, and you can find x values associated with specific probabilities. So you can either start out with an x value, calculate the z-score, and then find the probability of interest in the unit normal table, or you can start off with the probability of interest, like what score is at the 90th percentile, for instance. So that would be p equals 0.90 in the body. So you would take that probability, find that probability of 0.90 in the body, locate the z-score, and then use that z-score to calculate x. So whenever you're going between X and Z, and you can think about Z as like a bridge between scores and probabilities. So whenever you're going between X and Z, you need to use a formula. But whenever you're going between Z and the probability, then you're using the unit normal table. And you're going to get pretty comfortable with using this table through the examples in this lecture and your practice problems. And then here I just summarize what each of those columns in the unit normal table represent. So just some final notes. The unit normal table just provides close estimates. You'll notice that the z-scores in the unit normal table only go to the hundredths place. So if you calculate a z-score, like let's say you get 0.256, you would find z equals 0.26 in the table. You'd round it to the hundredths place. And it assumes a normal distribution. So if you have a situation where your data is not normally distributed, then that's going to be a problem, right? Because the unit normal table won't be very accurate. Now, if your data is close to normal distribution and you don't have access to the raw data, the unit normal table is probably your best option. But when you do have a normal distribution, the unit normal table is pretty darn accurate. And again, the unit normal table is great for situations when you simply do not have access to the raw data, but you still want to figure out the probabilities associated with specific scores or scores associated with specific probabilities. So let's do a bunch of examples. Now you'll see that on the lecture slides, all of these examples are presented to you. I'm going to actually do the work in a separate worksheet, so you're not going to have my work available to you. You're going to need to take notes. And I'm doing that to encourage you to write this out on your own. That helps you learn if you write things out instead of just sitting there and watching me do it. And I strongly encourage you to maybe after like the first example for finding probabilities of scores, using z-scores, after that first example, try the other three on your own. And then you can watch me do the first example of finding scores associated with probabilities, and then pause the lecture and try the last three on your own. Try it on your own while there's no consequences for not doing something correctly. It'll help you identify whether or not you truly understand what's going on in this material and help you correct those mistakes right here and now, even before you do practice problems in class. So I'm going to go ahead and exit the PowerPoint slides, and I'm going to do these examples in a little smart notebook here. All right, so now let's look at several examples of how to use the unit normal table. First, we're going to look at examples of how to use the unit normal table to figure out the probabilities associated with specific scores. And then the last set of problems will be looking at figuring out what set of scores fall within certain probabilities. So I encourage you, after I do this first example, to do the next three that are also related to finding probabilities associated with scores. So let's go ahead and go through this first example. All right. So we know, based on information from the Department of Motor Vehicles, that the average age of licensed drivers is 39.7. So that's our population mean. And that the standard deviation of that age is 12.5. So based on this, we know that, for instance, based on the empirical rule, we already know that 68% of drivers are between plus or minus 12.5 years from 39.7. So what would that be? Let's see. 39.7 minus 12.5. So between ages of 27.2 and let's see, 39.7 plus 12.5 and 52.2. So just pointing out, reminding you of the empirical rule, and that 68% of scores fall within one standard deviation of the mean. Okay, but the question that you're being asked is, what is the probability of randomly selecting a licensed driver who is older than 50 years old? Now that's the same thing as saying, what is the proportion of drivers who are older than 50? And so we're going to be looking at proportions in that unit normal table. But for this type of example, we're starting off with an x value. We are calculating the z-score for that x value, and then we're going to go to the unit normal table to find the proportion or probability. So the first step in this is we need to figure out the z-score for someone who is 50. So z when x equals 50. And remember, the z-score formula is x minus mu divided by sigma, or in other words, the score minus the population mean divided by the standard deviation. And the score of interest is 50. The the population mean is 39.7, and then the standard deviation is 12.5. So this becomes, and I do one step at a time, so 50 minus 39.7 gives you 10.3 divided by 12.5, and you have a z-score of 0.824. That is your z-score. Now, before I go to my table, I need to draw out my distribution to figure out, am I looking at a body, a tail, or a mean to z? So I'm going to go ahead and draw out this distribution. We're going to assume normal curves for all of these. And I'm going to go ahead and plot my x values and my z-scores. Now, the mean is always right in the middle of the distribution. So remember, when you're looking at a normal distribution, the mean, the median, and the mode are all the same value, and they're all right in the middle. And so our population mean is in the middle, so that's 39.7. And the z-score for the population mean is always 0, right? Because 39.7 is 0 standard deviations away from 39.7, the mean. And let's just for kicks go ahead and plot the -1 and +1 z-scores that I mentioned before. So that would be 39.7 minus 12.5, which was 27.2. And then 39.7 plus 12.5, the standard deviation, which was 52.2. All right. Now I want to think about the probability of randomly selecting a driver who is older than 50. So 50 would be like here-ish. And we want to know older than 50, so out here. And in drawing this out, I can pretty clearly see that we are looking at the smaller portion of the graph. So we are looking at a tail. So we're going to go to the unit normal table. We're going to find 0.82 in the table for z-score. Remember, it goes to the hundredths place, so we're just going to look for 0.82. We're going to round it to the hundredths place. So here's my table. Looking at the z column, right? Because that's what we're working with. That's what we know. We know that the z-score is 0.82. And boom, there's 0.82. This is the proportion in the body, or in other words, the proportion of scores with a z-score less than 0.82, or the proportion of scores less than 50. This is the proportion in the tail, what we actually want, right? The proportion of scores with a z-score greater than 0.82, or in another way we could say the proportion of scores or proportion of drivers older than 50. So 0.2061 is the answer that we're looking for. So based on this, we could say that 20.61%, right, if we take that 0.2061 and multiply it by 100, 20.61% of licensed drivers are older than 50. Or we could say there's a 20.61% chance of randomly selecting a driver from the population of drivers that's older than 50. Or we could just stick with the original question and say the probability of randomly selecting a licensed driver who is older than 50 years old is 0.2061. Alright, now go ahead and pause the video and try the next 3 problems on your own, because the next 3 problems are similar to the one that we just did, where we are starting off with an x value or a score, and we're trying to figure out the probability associated with that x value or a range of x values. Okay, so hopefully by this point you've already attempted the next 3 problems, and now I will go through and show you the answers. So this is a similar situation where we're starting off with x, we need to calculate z, and then we need to find p in the unit normal table. So the first thing we need to do is figure out the z-score associated with this x value of 30. So remember, the z-score formula is x minus mu divided by sigma, or the score, 30, minus the population mean, 39.7, divided by the population standard deviation, 12.5. So 30 minus 39.7 gives you negative 9.7. Divide that by 12.5, and you end up with a z-score of negative 0.776. Now remember, there are no negative values in the table, and the table only has z-scores up to rounded to the hundredths place. So we are going to be looking for 0.78 in the unit normal table. And before we look in the table, we need to determine what section of this distribution are we actually looking in. So I'm going to draw my distribution. Got my z-score of 0 in the middle that represents my population mean of 39.7. And we're looking for younger, or 30 years old or younger. So 30 would be roughly here. 30 or younger, that is going to be a tail. That is the smaller portion of the graph. So we look for 0.78 z-score in the table, and then we go over and look at the proportion in the tail. So z-scores, 0.78, proportion in the tail, right? Tail is 0.2177. That's your final answer. So we know the probability of randomly selecting a driver who is 30 years old or younger is 0.2177, or there's a 21, if we multiply this by 100, 21.77% chance of randomly selecting a driver who is 30 years old or younger, or we could say 21.77% of drivers are 30 years old or younger. Now let's look at the probability of randomly selecting a driver between 35 and 45. This one's a little bit trickier because we have two x values and we need to find the probability between them. So these are both x values in this case, but we are still taking an x value, converting it into a z-score using the z formula, and finding the probability associated with those scores. So let's go ahead and find the z-score when x equals 35 and the z-score for when x equals 45. And so x minus population mean divided by the standard deviation is 35 minus 39.7 divided by 12.5. 35 minus 39.7 is negative 9. Oops. No, it's not. So 35 minus 39.7 is negative 4.7 divided by 12.5. And you end up with a z-score of negative 0.376. Remember, in the table, there's no negative values, and we're rounding to the hundredths place. So this would be looking for 0.38 in the table for the z-score. Okay, let's find the next z-score. And I'm going to scoot it down a little bit, make myself some room. So the z-score for an x value, or a score, of 45. Still using that z-score formula. But now x is 45. We still are using the same population mean and standard deviation. So 45 minus 39.7 gives you 5.3. Divide that by 12.5, and you end up with a z-score of 0.424. And we're going to be looking for 0.42 in the table. When you're doing these for a quiz, make sure that you're writing out the actual z-score rounded to the thousands place. I'm just putting these little notes here just to show you exactly where we're going to look in the table in column A for our z-score. All right. Now, real quick, you can check your work to make sure that these make sense. This is a negative z-score, and that makes sense because 35 is below the mean of 39.7. 45 has a positive z-score, and that makes sense because 45 is larger than the mean of 39.7. And you can also see that these z-scores are relatively small because 35 and 45 are not that many standard deviations away from the mean. Or in other words, not that many, they're not even 12.5 away from 39.7. So let's go ahead and draw our distribution out just to visualize what we are actually looking for. This time I'll put my x values on the top and my z on the bottom. So again, our population mean is still 39.7, z-score of 0, and we are looking for the probability of randomly selecting a driver between 35 and 45, and we have identified those z-scores as negative 0.376 and 0.424. And again, 35 is less than the mean, negative z-score, 45 is greater than the mean, positive z-score. And let's go ahead and shade in that space of interest. There's multiple ways that you could find this. You could look for the proportion in the body for a z-score of 0.42 and subtract the proportion in the tail for a z-score of 0.38, and you would be left with this. You could take the proportion in the body for a z-score of 0.38 and subtract the proportion in the tail for a z-score of 0.242. But I'm only going to demonstrate the easier way, in my opinion, to do this, because anytime you're looking for the probability of randomly selecting a range of scores where the mean is in the middle, you can simply take the mean to z's for each and add it together. So we'll take the proportion of scores between the mean and a z of 0.38 and add that to the proportion of scores between the mean and z equals 0.42. So if we color code this, that would be this, and that would be this section of the graph. Just add those two together and you get exactly what you are looking for. So let's find z of 0.38 in the unit normal table. 0.38, mean to z, 0.1480. So we have 0.1480. We're going to add that to the proportion between the mean and a z-score of 0.42. Find the z-score of 0.42, mean to z, 0.1628. And you end up with 0.3108 as your final answer. So just breaking this down, if we turn it into percentages, 14.8% of drivers are between 35 and 39.7. 16.28% of drivers are between the age of 39.7 and 45. Add those two together, and you know that 31.08% of drivers are between age 35 and 45, or we could say there's a 31.08% chance of randomly selecting a driver between 35 and 45, or the probability of randomly selecting a driver between 35 and 45 is 0.3108. Now this one's a little bit trickier because you don't have a situation where the range of scores, one is below and one is above the mean. But we still are taking x, turning it into z with the formula, and then finding p in the table. And again, just like the last example, we have two x values. Now we've actually already found these z-scores. So z, when x equals 45, we found that in the last problem, right? So I'm just going to go ahead and write down that we already know it's 0.424. And then the z-score for when x is equal to 50, I already found that in the very first problem that we did. So you can see here that when x is 50, the z-score was 0.824. And so here we're going to be looking for 0.42 in the table, and here we're going to be looking for 0.82 in the table for the z-scores in column A. Let's go ahead and sketch this out to determine what it is we are actually going to be looking for. So we've got our x values, our z-scores, 39.7, population mean in the middle, z-score of 0, and we're looking between 45 and 50. So this area here. Now there's three different ways that we could find this, just like in the previous example, but there's really no one way that's the most simple in this case because we don't have a situation where one scores below the mean and one scores above. So I'm going to show you all three ways, and you're going to get the same answer all three ways. So if you want to try, just for practice, to do body minus tail or body minus tail here, you will get 0.3108. But I'm going to show you all three ways on this example. All right, so we could take, and let's draw our z-scores in as well. So for 45, it was roughly 0.42, 50, 0.82-ish. All right, so we could look for the proportion in the body for a z-score of 0.82, subtract the proportion in the body for a z-score of 0.42. Or we could take the proportion in the tail for a z-score of 0.42 and subtract the proportion in the tail for a z-score of 0.82. And even yet another way we could do this, we could find the proportion between the mean and a z-score of 0.82 and subtract the proportion between the mean and z for 0.42. So I'm going to write these out in symbols. So we could take the proportion in the body for z of 0.82 and subtract the proportion in the body for z of 0.42. Remember, this would be a body because it's the larger portion of the graph. Or we could find the proportion in the tail for a z-score of 0.42 and subtract the proportion in the tail for a z-score of 0.82. And then finally, we could use the mean to z column and take the proportion mean to z of 0.82 and subtract the proportion between the mean and z of 0.42. So let's go ahead and find our values corresponding to a z-score of 0.42 and plug those into all of these equations here. So z, 0.42, in the body, 0.6628, in the tail, 0.3372, and then mean to z, 0.1628. So I'm going to go ahead and fill those in here. All right. So we had, let's see, in the body for a z-score of 0.42 was 0.6628. In the tail for 0.42 was 0.3372. And then mean to z for 0.42 was 0.1628. All right, now let's look at the values, body, tail, mean to z for a z-score of 0.82. Body, there's z, 0.82, the body, the tail, and the mean to z. So let's go ahead and sketch those in here. So the body with z of 0.82 was 0.7939. The tail for 0.82 z-score was 0.2061. And then mean to z for a z-score of 0.82 was 0.2939. And for all of these, you are going to find the answer of 0.1311. So 13.11% of drivers are between 45 and 50. You have a random chance or a probability, if you randomly select a driver, you have a 13.11% chance that they'll be between 45 and 50, and the probability of randomly selecting a driver between 45 and 50 is 0.1311. Now, when you do this in practice, you don't have to do it all three ways. I just showed you all three ways so that you would get a lot of exposure to how you can use that unit normal table to find what you're interested in. You use whichever one makes the most sense to you, whichever one you're most comfortable with. So now we are kind of flipping the situation. Whereas before we started off with x, we found the z-score using the z-score formula, and then we found p. Now we're starting with p, the percentile, which can be converted into a proportion or probability by just dividing it by 100. And we're going to find z in the table and then use z to calculate x using the x formula. So what score is at the 85th percentile? Well, when you think about percentiles, and you've been exposed to this already, that tells me what score separates the bottom 85% from the remaining top 15%. And you can think about the fact that the unit normal table represents a normal curve. And in a normal curve, your mean, median, and mode are the same value right in the middle. And your median separates the top 50% of scores from the bottom 50% of scores. So your percentile at the mean is 50. And then as you go to the right, you're increasing, right? So bottom 60% from the top 40%, bottom 70% from the top 30%, bottom 80% from the top 20%, bottom 90% from the top 10%, and then once you get to the 100th percentile, that means that that is the highest score possible. So 100% of people, if we're looking at SAT scores and we're looking at the 100th percentile, 100% of test takers had a score that's at that position or lower. Then as you go, so all these values that you see here, all these percentiles, these represent scores that are greater than the mean. And then to the left represents scores that are less than the mean. So then we just gradually decrease. So a score at the 10th percentile separates the bottom 10% from the top 90%, for example. So whenever you see percentile, you can think about the bottom whatever percent, right? Bottom 85%. So that score would be like here-ish. And this would be like P equals 0.85 in the body. And then this piece right here would be P equals 0.15 in the tail. Now it's important that you sketch this out so that you know if the z-score that you're looking for in the table is positive or negative. Remember, there's no negatives in the table. So you have to know if my score falls to the left of the mean, if my score is less, or sorry, if my percentile falls to the left of the mean, then I know that my z-score is going to be negative and my x value that I calculate is going to be less than the mean. If my percentile falls to the right of the mean, then I know that my z-score is going to be positive and my x value or my score is going to be greater than the mean. Now, there's kind of some shortcuts to drawing the picture, although I encourage you to draw it out. First of all, you know you're looking in the body if you're looking at the 85th percentile, because you're never going to have a p-value in the tail that's 0.85, right? Think about it. This entire graph represents a p-value of 1 or 100%, right? 100% of the scores, or probability of 1 of selecting any given score, right? So when you think about body versus tail, and let's go ahead and take a look at the unit normal table, you can see that when you add the body to the tail, you get 1 every single time because that represents the entire distribution. You can also see that the starting point for body and tail is 50% or 0.50 p-value, and it gets lower for the tail and it gets higher for the body. So you know, for instance, that you're never going to have 0.496 in the body because that is the smaller piece of the graph. That's 49.6% of the graph, and that leaves what? 50.4? Yeah, 50.4%, which would be, oh, there it is. I don't even know I was doing head math. It's right there in the body. Just like you know, you're never going to have, for instance, 0.508 in the tail because that's always going to be a bigger portion than what's left. So some shortcuts again. You can look at this and you can say, I know I'm going to divide, if I'm looking for a percentile, I'm going to divide this by 100 to get my p-value. And you should know that your p-value is never, ever, ever going to be in a body if it's less than 0.50. And it's never going to be in the tail if it's greater than 0.50. So I look at this, I know that P equals 0.85. I automatically know if I'm looking at 85% of the distribution, I'm looking in the body. And I can also look at this and think, okay, well, if it's 0.85, that means that it's greater than 50, and that also means that my score is going to be to the right of the mean, so I'm going to have a positive z-score. Okay, so now we need to actually find 0.85 in the body in our graph, or in our table. So proportion in the body. We're looking for 0.85. And one of the tricky things with this is that you're not going to usually find exactly what you're looking for, right? You're not going to find 0.85 exactly. But you will look for the one that's just below the one you're looking for and the one that's just above the value that you're looking for. And then you'll decide which one is closer. Well, if you took 0.85, right? We're looking for 0.85 in the body. If you took 0.85 and subtracted this, you'd get 0.0015. If you took 0.85 and subtracted this, you would get 0.0008. This one is closer, right? This one is fewer points away from 0.85, so this is the z-score that you would go with. Now similarly, if you were going to go the route of looking for 0.15 in the tail, right? Because 1 minus 0.85 gives you 0.15, so that's what's left. It's kind of like the complement rule that you've learned about before. If you go, I'm going to look for 0.15 in the tail. You look for the one just above 0.15, the one just below 0.15 in the tail, and go with the one that's closer. This one is still closer. You still land on a z-score of 1.04. And you know that the z-score in question is positive because you know that it's falling to the right of the mean. So if I wrote in my z-scores, this would be a z-score of 0. This would also have an x value that's equal to the mean if we're looking at that. So remember, these are my percentiles. And we just found our z-score of 1.04. That's the z-score at the 85th percentile, but we want to know the x value, or just the regular old score at the 85th percentile. So we need to convert that z-score into an x value using the x formula, which is equal to z times the standard deviation plus the mean. Now, if you're wondering where this formula was derived, it's derived from the standard deviation formula. So, I'm sorry, the z formula. So if you think about the z formula, z is equal to x minus mu over sigma, or the score minus population mean divided by the population standard deviation. We can algebraically manipulate this equation so that we're left with x equals something. So we want to get rid of this division here. We want to get rid of the standard deviation, so we multiply both sides by the standard deviation. Remember, if you do the same thing to both sides, it doesn't change the overall value of the equation. So then this becomes z times the standard deviation equals x minus mu. And then we want to get x all by itself on one side of the equals sign. So we add the mean to both sides. We're getting rid of it over here, but we're adding it over here. And you are left with this equation. Now that's not that important for you to remember as far as your grade goes, because you can just jump straight to this x formula once you find your z-score. So this equals 1.04 times the standard deviation plus the mean. 1.04 times 100 is 104. I should probably replace that m with a 500. There we go. Add 500 and you get 604. I'm going to go ahead and fill that in my little graph here. So I know that a score of 604 is at the 85th percentile. Put another way, I know that if I randomly selected a score, I would have an 85% chance that that score would be 604 or less, and a 15% chance that that score would be greater than 604. You could also think about it this way. 85% of SAT takers had a score less than or equal to 604, and 15% of test takers had an SAT score greater than 604. Alright, so now I've showed you how to go from a p-value to an x value using z as like the little bridge between. And remember, whenever you go between x and z, you use a formula. Whenever you go between z and p, you use the table. Go ahead and give the last 3 problems a try on your own. Pause this video and try to work through those last 3 problems using the same sort of process. Alright, so now let's go ahead and go over the answers to the problems that hopefully you already attempted on your own. So what SAT scores at the 80th percentile? So I know that I'm looking for 80 divided by 100 equals P of 0.80, and I know I'm looking in the body because this value is greater than 0.50, and I also know that I'm looking at a positive z-score because this value is greater than 0.50. But I'm going to go ahead and sketch this out anyway. So I know that a value at the 80th percentile separates the bottom 80% from the top 20%. So we have P equals 0.20 in the tail to the right. And then the rest, P equals 0.80 in the body to the left. So I could either look for p equals 0.80 in the body or p equals 0.20 in the tail, and I'm going to wind up with the correct z-score. So let's go ahead and look for it. Okay, proportion in the body, let's look for 0.80. This one's just above 0.80, this one's just below. This one is closer to 0.80 than this one. And if we're looking for 0.20 in the tail, this one's just below, this one's just above, and this one's also closer, right? These are both closer to the values of interest. 0.80 in the body, 0.20 in the tail. 0.84 is my z-score. So we've got our z 0.84. And we know the middle is 0, and we know that corresponds to an x value that's equal to the population mean. Okay. But that's not what we're being asked to find, right? You're being asked to find the SAT score. But you can use the z-score to figure out the SAT score using the x formula. So now we have 0.84 times 100 plus 500. So this becomes 84 plus 500. 584 is the value right here. That is x. So if we wanted to interpret this, we know that a score of 584 is at the 80th percentile. So 80% of test takers had a 584 or lower, and 20% of test takers had a score above a 584. Now we want to figure out what score is at the 25th percentile. Well, remember, to get a p-value out of percentile, we just divide by 100, and we get p equals 0.25 in the what? Well, you should know, if you think about it in terms of percent, 25% of the graph is the smaller portion of the graph. It's a p-value less than 0.5. So we automatically know that we're looking at a tail. We can also look at this and realize that our percentile is less than the 50th percentile. Our p-value is less than 0.25 for our percentile. So we know that we are working with a negative z-score. Now, this rule doesn't work about negative or positive unless you're working with percentiles. So be really careful. Because if I say I'm looking at the top 25% of scores, then you would say, oh, 25%, that's less than 50, it's negative. But I'm actually looking for a score to the right of the distribution, right? The top 25% would be a score at the 75th percentile, for instance. Okay, so just be careful. I'm just trying to give you shortcuts, not confuse you. So a score at the 25th percentile separates the bottom 25% from the top 75%. So we would have p equals 0.25 in the tail here. Or we could look for p equals 0.75. Whoop, that's a 9. 0.75 in the body. Whichever. We're looking for the score that separates the bottom 25% from the top 75%. And we are still going from p to z to x. So let's go ahead and consult our unit normal table. I'm going to go ahead and look for p equals 0.25 in the tail. And I'm going to go find the one that's just above 0.25 and the one that's just below. This one's 0.0017 points away from 0.25. This one's 0.0014 points away from 0.25. So I know I'm going to go with the z-score in this row, right? We're going to go over to z and find z. If you're looking for 0.75 in the body, this is the closest value to 0.75. So you would still land here at 0.67. Drawing your graph helps you realize once you get to this point that it's not just any old 0.67, right? It's negative 0.67 because it's a score that's to the left of the mean. So we know that the score we're looking for is going to be less than 500. So when we plug this value in to our x formula, we get negative 0.67 times the standard deviation of 100 plus the mean of, oh, there I go writing mu again. We know what the mu is, it's 500. So we have negative 67 plus 500, and we end up with a value of 433. So that goes right here in our graph. So 25% of test takers had a score of 433 or less. 75% of test takers had a score above 433. If we randomly selected an SAT score, we would have a 25% chance of randomly selecting a score of 433 or less, and a 75% chance of randomly selecting a score greater than 433. That's all coming from that same calculation. Now let's do one that's a little trickier. Now we're looking for the middle 50% of the distribution. We're not looking at a percentile anymore, so you really have to think this through and visualize what this would look like on your graph. We're starting with P, we're finding Z in the table, and then we're calculating X. But we need to know where to start with our p-value. Well, you can think about the normal distribution as quadrants with 0.25, 0.25, 0.25, and 0.25, right? Add those together, you get 1. I just split it up into quarters or quadrants. Well, if we're looking at the middle 50%, we're looking for the two scores right here. And those two z-scores are going to be the exact same z-score, it's just one's going to be negative and one's going to be positive because they're both 0.25 p-value away from the mean in the middle. They're the same distance from the mean. You could also think about this. Well, let's go ahead and strategize with this way right now. So what we could do is we could find P. Actually, let's write it this way. We could find the z-score that corresponds to P equals 0.25 mean to z, right? So looking for this, the z-score right here, which is going to be the same, just the negative version of the z-score right here. Or you could look for the z-score that corresponds to P equals 0.25 in the tail, because we have 0.25 in the tail adjacent to the z-score location we're interested in. Or you could look for z P equals 0.75 in the body. So, right, 0.25 plus 0.25 plus 0.25 is 0.75. So the body to the left would be at a z-score here, 0.75 in the body to the left. And then 0.75 in the body to the right, 0.25 plus 0.25 plus 0.25, would land you at this z-score here. Either way you go, you're going to end up with the same exact z-score. And let me show you. So, if we're looking, let's go ahead and start with mean to z, because to me that makes more sense. We're looking for 0.25 mean to z. This one's just below, this one's just above, and this one's closer. Well, guess what? This is closest to 0.25 in the tail, and this is closest to 0.75 in the body. No matter which way we think about it, we land on a z-score of 0.67. And it's not just 0.67. Remember, we have one on the left and one to the right of the mean, so we have negative 0.67 and positive 0.67 for our z-scores. And remember, 0 is in the middle. So now let's go ahead and figure out what is the two x values that separate the middle 50% of the distribution. Remember, we know that our mean in the middle is 500. Okay, so we need to figure out the x for z equals negative 0.67 and x when z equals positive 0.67. Now, remember, we just found the score at the 25th percentile that separates the bottom 25% from the rest of the distribution. And remember, that z-score was negative 0.67. So I already found this value. It's 433. So I'm just going to go ahead and plug that in. Now let's figure out the value for a positive 0.67 z-score. So x times standard deviation. Oh, sorry. Z times the standard deviation. My bad. Z standard deviation plus the mean. 0.67 times 100 plus 500. This becomes 67 plus 500, and you get 567 That is the x on the high end of this. So 433, 567. So these two things would be your final answer. So we can say 50% of SAT scores are between 433 and 567. We could also say 25% of SAT scores are between 500 and 567, and 25% are between 433 and 500. If we randomly selected a score from the SAT scores, we'd have a 50% chance that that value would be between 433 and 567. So I hope that you feel quite ready to do these things on your knowledge checks and practice problems and on your own. And I went through a lot of examples just because I want you to have a lot of practice with using the unit normal table to find these values and to really be able to visualize how you can see what kind of p-value you're looking for in the table, be it a mean to z, a tail, or a body.